Hello everyone. In this video we will see a very important concept, that is the concept of rotation of complex number. See, z equal to x comma y, that is x plus iota y, is any complex number in Argand plane. So what do you mean by the rotation of this complex number z? Okay, x comma y. So I want to rotate this complex number z. The question is that how I can rotate it, about what point I can rotate it. That is important. Now for this, you have to understand the concept of vector algebra. In vector algebra, what happened? This is your point P having the coordinate x comma y. This is y axis and this is x axis. So then this vector OP is a vector given by xi plus the yz, where I is a unit vector along x-axis and j is a unit vector along y-axis, and the modulus or magnitude of this vector OP, magnitude means the length of this vector OP, is given by square root of x square plus the y square, that is magnitude of OP. So we know this. You can say that this is an arrow initiated from point O and the terminal point is P. So this is an arrow. This is a vector. Vector is represented by xi plus yj, where I and j are unit vectors along x-axis and y-axis respectively. And the length of this vector or length of this arrow, that is the magnitude of this vector, is given by square root of x square plus y square. Very easy. Okay, this distance is x, this distance is y. Therefore, by applying the Pythagoras theorem, this distance or modulus or magnitude of vector OP is square root of x square plus y square. Now, coming to the Argand plane. This is the Argand plane. We are having the complex number z, x comma y. So, what do you mean by the modulus of z? The modulus of z is square root of x square plus y square, and modulus of z is distance of z, okay, from origin, and z is a complex number. This point P is there, okay, this point P is there, which is represented by the complex number z, that is x comma y, that is x plus iota y. So every complex number can be represented by vector OP. Every complex number can be represented by a vector. So this OP vector represented by this complex number z, and the length of this arrow is given by modulus of z, and modulus of z is square root of x square plus y square. In vector algebra, the magnitude of vector OP is again a square root of x square plus y square. Therefore, we can say that every complex number in Argand plane can be represented by a vector. Now here comes the concept of rotation. So rotating a complex number, in fact rotating this vector. Okay, rotating a complex number means we have to rotate this vector OP. Now we can rotate the complex number z about the origin here. Okay, we can rotate the complex number z either anti-clockwise or clockwise direction by some angle theta. Correct? Now, but we also know that every complex number can be represented in three ways. Okay, what are those three ways? Z can be represented in three ways. Okay, Z is Cartesian form. This is x comma y, that is x plus iota y. This is your Cartesian form. I can write down z as r into cos theta plus I sin theta. Okay, where r is modulus of z, that is square root of x square plus y square in this way, and theta is your principal argument tan inverse of y by x. This is your principal argument. The principal argument always lying between minus pi to pi including pi. Okay, and the third form which is important here, that is z equal to r into e iota theta. This is called as a Euler form. This is Euler form of complex number. Complex number, where r is modulus of z and theta is its principal argument. Correct? So we will use this Euler form to understand the concept of rotation of complex number. Means this complex number z has to be written in Euler form. Okay? And rotating the complex number z means we have to rotate this arrow OP, this vector OP. Okay? So first, I will write down this complex number z in Euler form. So let the modulus of z, suppose this is a circle and this is your vector OP. This P is represented by the complex number z, and this vector OP is making angle theta 1 with the positive direction of x-axis. Correct? This is y-axis. In argon plane we call x-axis as the real axis and y-axis as the imaginary axis. Correct? So I can write down this vector z as modulus of z into e iota theta 1. Modulus of z, I can put any real number, say r, I can write down. I can write down this is r into e iota theta 1. So z can be represented in Euler form as r into e iota theta 1. Okay. That means the argument of this complex number z is theta 1. Modulus of this complex number z is r. Therefore, I can write down z as r into e iota theta 1 by using the Euler form. Okay, fine. Now here comes the concept of rotation, that if I rotate this complex number through an angle theta degree and anti-clockwise direction. So I am getting this row, this arrow, this is say OQ. OQ is something like that, Z1. The complex number is Z1. Here the complex number is Z. Here the complex number is Z1. That point Q is represented by a complex number Z1, which is obtained. This point Q is obtained by rotating. Okay, by rotating this vector OP. That is, I am rotating the complex number Z, or you can say that rotating the arrow OP, okay, by theta degree anti-clockwise direction. So now see, the modulus of both the complex number Z and Z1 are same, but the argument of this complex number Z1 is theta plus theta 1. Argument of Z1 is theta plus theta 1. So therefore I can write down Z1 as modulus of Z1 into E iota theta 1 plus theta in Euler form. Modulus of Z1 is modulus of Z. Here I am simply rotating the complex number. I can stretch the complex number after rotation. I can compress the complex number after rotation. But here simply we are rotating the complex number. So this is R into E iota theta 1 into E iota theta. This E into iota की E की power में iota into theta 1 plus theta can be written as E iota theta 1 into E iota theta. Okay. Now look at here. This R into E iota theta 1 up to this. This R into E iota theta 1. R into iota theta 1 is Z. So Z1 can be written as Z into E iota theta. This is the important result to understand the rotation concept. Now you can very easily understand the rotation concept. What we are observing here, this z is a complex number, okay, and we got this complex number z1 after rotating this complex number z anti-clockwise direction by theta degree, correct? So this z1 can be written as z into e iota theta. So when z is multiplied by e iota theta, we are getting z1. So z1 is the resultant of rotating complex number z through theta degree anti-clockwise direction, correct? So therefore this e iota theta, you can say that is a rotating factor. So when I multiply it by e iota theta to any complex number z, that means the z is being rotated theta degree anti-clockwise direction, because e की power iota theta, we are now observing that it is just a rotating factor. When it is multiplied by this complex number z, z is being rotated through theta degree anti-clockwise direction, and its new position is z1, which is given by z into e की power iota theta. Okay, fine. Now from here I can also write down z1 by e की power iota theta equal to z. So this we can write down z1 into e की power minus iota theta, that is equal to z, correct? From here I can write down this one. So again you are observing here that we are multiplying this z1 by e की power iota minus iota theta, and we are getting the complex number z. So e की power minus iota theta is actually the rotating factor for this complex number z1, that z1 is being rotated clockwise direction theta degree. z1 is being rotated clockwise direction theta degree to get its new position z. So finally e की power iota theta, you can say that it is a rotating factor. If theta is positive, the complex number rotated anti-clockwise direction, and if theta is negative, the complex number is rotated in clockwise direction, correct? So this is the first concept in the concept of rotation of complex number. Now coming to the second one. Second one, what is that? See, this is the complex number z, because every complex number is represented by a vector. So this vector OP, this point P is represented by the complex number z. The z is given by x plus iota y in Cartesian form, but if its argument is theta 1, correct? Its argument is theta 1 and modulus is r, then I can write down z equal to r into e iota theta 1, that we all know. Now I am rotating this complex number and we are getting this complex number z1, correct, which is represented by the vector OQ. So this is the vector OP, this is the vector OQ, and clearly you can observe that here after rotating the vector OP or arrow OP, we have stretched the vector or the arrow OP to get OQ. Okay, rotation and stretching both are doing. So OP vector is being rotated by say some theta degree, by theta degree anti-clockwise direction, and we are stretching it. At the moment you can see that the length of both the arrow is not same. The length of both the vector is not same. The modulus of both the complex number is not same. Correct? So here what happens? See, this is OQ vector and this is your OP vector. Correct? When OP vector is divided by magnitude of OP vector, it becomes the unit vector. And when OQ vector is divided by magnitude of OQ vector, it becomes the unit vector. So now we are rotating the unit vector along OP vector. We are rotating the unit vector along OP vector theta degree anti-clockwise direction. E की power iota theta is the rotating factor. So when we multiply this unit vector with e की power iota theta, we will get this unit vector. Correct? So you can now say that this OP vector, that is z complex number divided by magnitude of z complex number multiplied by e iota theta, we get the complex number z1, okay, divided by modulus of z1. So this is the second concept of rotation theorem. So when their length are not same, when we are stretching the complex number or we are compressing the complex number after rotation is done, then we can stretch the complex number or we can compress the complex number. Then we have to find out the new position. The new position is given by this formula. Correct? Okay, fine. Okay, no problem with that. Now coming to the third position. Here in both the cases we have observed that we are rotating the complex number about origin only. Correct? Now if third one is, see, this is the organ plane and this is the, okay, this is the arrow. So this arrow is given by z minus z naught and its length is given by mod of z minus z naught. So the vector is represented by, this vector is represented by z minus z naught. So if suppose that it is making angle theta 1 degree with the positive direction of x-axis, then this vector z minus z naught is given by z minus z naught ka magnitude e iota theta 1. And now it is being rotated, okay, by theta degree to get this another arrow. This another arrow is, suppose that this is z1. So this z1 minus z naught is modulus of z1 minus z naught e iota theta plus theta 1. Correct? Because the argument of this arrow or this complex number z1 minus z naught is theta plus theta 1. So here, if I don't know whether it is the length of this, both the vectors are same or not. So therefore I will rotate the unit vector along these vectors. So therefore I can write down, what I can write down? I can write down simply z minus, this is z1 minus z0 divided by, this is z1 minus z0, okay. This is what? E की power iota theta 1 into e की power iota theta. Correct? E की power iota theta 1 I can write down from here. What is that? This is z minus z naught divided by modulus of z minus z naught into e की power iota theta. z1 minus z naught magnitude z1 minus z naught is equal to z minus z naught divided by magnitude of z minus z naught into e iota theta. Here also you can observe that this e की power iota theta is the rotating vector by which we are rotating this arrow theta degree anti-clockwise direction to get this arrow, and this arrow is represented by this complex number z1 minus z0, and we are rotating the unit vector along this arrow. Correct? If the length of both the vectors are same, then this will get cancelled out with this, and we will remain with z1 minus z0 equal to z minus z0 equal to e iota theta. This is the original arrow and this represents the final arrow after rotating this arrow anti-clockwise direction theta degree. Correct? And the last concept in the rotation of complex number, what is that? See, if we are having these are two vectors, say a z1 and this is bz2, and this is the vector. So AB vector is being rotated to get that CD vector. C is Z3, D is Z4. Now this vector is being rotated theta degree about this point of intersection. Say this point is anything, say P. Okay. So we are now rotating this vector AB theta degree anti-clockwise direction to get the vector CD. So therefore, this CD is your resultant vector, and which is obtained by rotating this AB vector through theta degree. But anti-clockwise direction. But we don't know about their magnitude. So therefore, this is unit vector. Now rotating. Unit vector. Now we are rotating along this AB vector to get the unit vector along this CD vector. Correct? So I can write down this CD vector as CD. This is Z4 minus Z3 modulus of Z4 minus Z3, and this is AB vector. AB vector is Z2 minus Z1 by modulus of Z2 minus Z1 into e की power iota theta. So that means you are rotating the complex number either about the origin, number 1 point, or you are rotating the complex number about some fixed complex number like that Z0, correct? And the third one is here the two vectors are rotating about their point of intersection. Here also we can apply the concept of rotation theorem. Now again we will try to understand it deeply, the concept of rotation theorem. See what happens. This is your complex number Z given by r into e की power iota theta. We are rotating this complex number Z by theta degree anti-clockwise direction to get the new complex number Z1, which is given by r into e iota theta 1. This is iota theta. This is suppose theta 1. This is the theta. Then Z1 is r into Z1 is Z into e iota theta. Correct. So Z is multiplied by e iota theta. It means that Z is being rotated to get the new position as the Z1. Okay. Z is given by r into e iota theta 1, where r is the magnitude of model this complex number Z. Theta 1 is argument of this complex number Z. Okay, fine. But can you observe here that this theta is the angle between these two vectors? Theta is the angle between these two vectors. Now see, if I say that argument of Z1, this is super important. Argument of Z1 is theta plus theta 1. That is, argument of Z1 is theta plus argument of Z. Correct? So argument of Z1 plus theta is your argument of this Z plus theta is your argument of Z1. And alternatively you can say that the angle between Z1 and Z is theta. So observe this very clearly, that we are having argument of Z1 that is equal to theta plus argument of Z. Or you can also write down argument of Z1 minus argument of Z equal to theta. Or you can also write down argument of Z1 by Z is theta. So you have to understand it, that argument of Z1 equal to argument of Z plus theta, that is the angle between Z and Z1 is theta. Argument of Z1 minus argument of Z equal to theta, that is the angle between Z and Z1 is theta. Or theta is being rotated anti-clockwise direction. Complex number Z is being rotated anti-clockwise direction theta degree to get the new complex number Z1. Like that you have to understand it. And there are some special cases. See, we know that e की power iota x is given by cos of x plus iota का sin x. So therefore e की power iota pi is cos pi plus iota sin pi. Cos pi is -1, sin pi is 0. So e की power iota pi is -1. This is a very famous Euler's identity. Okay, e की power iota pi plus 1 equal to 0. Euler's identity. Second, if e की power iota pi by 2 I to find out, this is cos pi by 2 plus I sin pi by 2. Cos pi by 2 is 0, sin pi by 2 is 1, this is equal to iota. E की power minus iota pi by 2 is cos pi by 2 minus pi by 2 plus I sin minus pi by 2. Cos of pi by 2, this is simply pi by 2, okay. Cos is a even function, no? Cos is even function. So therefore cos of minus of angle is equal to the cos of angle only. And this minus will come out minus I sin pi by 2. So this becomes minus iota. So e की power iota pi by 2 is iota. E की power minus iota pi by 2 is minus iota. Similarly, we can have like that. E की power iota 2 pi by 3. Okay, 2 pi by 3. So this is cos 2 pi by 3 plus iota sin 2 pi by 3. This is cos pi minus pi by 3 plus iota sin pi minus pi by 3. Now coming to the trigonometry, pi minus pi by 3, it means that it is second quadrant, so minus cos of pi by 3. Correct? So this is minus cos of pi by 3 and this is plus I sin pi by 3, because sin pi minus pi by 3 in second quadrant sin is positive and cos is negative. Okay, so this is pi by 3 means minus 1 by 2 plus iota root 3 by 2. So e की power iota pi by iota 2 pi by 3 is your minus 1 by 2 plus iota root 3 by 2, and that is actually the omega. This is the omega complex number. And similarly I can have e की power minus iota 2 pi by 3 is equal to minus 1 by 2 minus iota root 3 by 2, that is equal to omega का square. So these standard result that e की power iota pi by 2 is iota, e की power minus iota pi by 2 is minus iota, e की power iota 2 pi by 3 is omega, e की power minus iota 2 pi by 3 is omega square. So these results you have to understand. Okay, e की power iota pi is minus 1. So directly now you can get the result. First one is, if z is multiplied by e iota pi by 2. So what do you understand by this? That z is being multiplied by e की power iota pi by 2. That means z is being rotated through 90 degree anti-clockwise direction to get the new portion, and the new portion is given by e की power iota pi by 2 is iota z into iota, that is iota z. So this is the new portion when we are rotating complex number z. Okay, like that. This is your z and this is your iota z, and rotation is 90 degree anti-clockwise direction. Similarly, if I said z into e की power minus iota pi by 2, then I will get the new portion is the minus iota z. Same, z is multiplied by e की power iota 2 pi by 3, then the new portion is given by z into omega. Fourth, z into e की power minus iota 2 pi by 3, new portion is given by z into omega square. Now one more important concept. Now look at here, this z and iota z, the angle between z complex number and iota z complex number is 90 degree, and modulus of both z and iota z is same. Modulus of iota z is modulus of iota into modulus of z. Modulus of iota is always 1. This is simply modulus of z. So if we are having any triangle, okay, if we are having any triangle having the vertices as a z, b iota z, and c iota plus z, iota z plus z, c, find the area of triangle ABC formed by AZ, B iota z, and C z plus iota z. We have to find out the area of this triangle. Okay, fine. See, we know that This is the complex number z. This is the complex number iota z. Angle between them is 90 degree. Okay, clear? Now what about this z plus iota z? As I said earlier that every complex number is represented by a vector. So the parallelogram law of vector addition is also valid over here. The parallelogram law of vector, the resultant vector, you can say that. See, the resultant vector is given by, here we will have, this is, okay, we can construct a parallelogram, and this resultant vector is given by z plus iota z, okay, by parallelogram law of vector addition. In vector, what happens? This is your vector A, this is your vector B. So we construct a parallelogram, okay. So this is your resultant vector. This resultant vector is given by vector A plus vector B, correct? Similarly, here we are having the vector represented by complex number z. Here another vector represented by the complex number iota z. So the resultant vector is represented by the complex number z plus iota z, which is clearly obey the parallelogram law of vector addition. But here we have to find out the area of the triangle ABC formed by these 3 points. So how to do that? So see, we have to find out the area of this triangle. Okay, we have to find out the area of this triangle. But this triangle area is same as the area of this triangle. So area of triangle ABC is area of this triangle. And this triangle area can be found out very easily because it is a right angle. This is modulus of z, this side is modulus of z, this side is modulus of iota z, which is equal to the modulus of z. So area is half into base into height, that is half into modulus of z ka square. So I hope that you understand each and every concept related to the rotation of the complex number. In fact, rotating a complex number means we are rotating a vector. But we can rotate the complex number about origin, or we can rotate the complex number about some fixed complex number. And we can also rotate the complex number clockwise, and we can also rotate the complex number anti-clockwise, and the rotating factor is e की power iota theta. Correct? When a complex number is multiplied by e की power iota theta, that means we understand that the complex number z is being rotated theta degree anti-clockwise direction to get its new position. Correct?